Hi everyone, it's still me. I'm Reiju from Carnegie Mellon University. I'm presenting on behalf of Chen Huang, and this work is about learning policy for adaptive tracking with deep feature cascades. So our motivation is that visual object tracking is a time-critical task. So existing shallow tracking methods use correlation filters, which are real-time on CPU. While deep methods usually achieve top performance, they need a high-end GPU, and some of the state-of-the-art deep trackers are not even real-time on GPU. So our goal is to learn to improve the speed of deep trackers without losing any accuracy. So the idea is to take an adaptive approach with deep feature cascades. Ideally, easy frames are processed with cheap features, like pixel values or hog features, and challenging frames are processed with invariant but expensive deep features. So this turns our adaptive tracking problem into a decision-making process. We propose to learn an agent to decide whether to locate objects on an early layer of a deep network or continue to processing in subsequent layers, or even simply use hog or pixel values. Obviously, this will significantly reduce the feed-forward cost for easy frames. So this figure shows our framework for policy learning. We use the Siamese FC network architecture, and at each layer, we evaluate the template score map and feed it into the Q network to make decisions. We also define two pre-layers of pixel values and hog features, so as to use fast correlation filters to compute their scores. For policy learning, we use the deep Q learning technique. We define actions as 7 box scaling transformations and 1 stop action. States are the score map history and action history. So during testing, we simply apply the policy for each frame. And we refer to our approach as early stopping tracker, or EAST. And this figure shows the layer stopping probability of EAST. We found most frames are indeed quite easy to track. So pixel values or just hog layer may just suffice for these frames. And obviously, the lower layer stopped, the higher speedup achieved. And as a result, we achieve 10 times speedup over baseline deep trackers on average, and up to 100 times speedup for almost half of the frames, which is 190 FPS on CPU. And this makes EAST the fast CPU, the fast and the first CPU-friendly deep tracker. And we quantify our tracker on 4 benchmarks and show state-of-the-art accuracy with fast speed. Sometimes we can even observe improved accuracy because each feature layer of our network is also updated during training. So finally, take-home message. Learning an agent to choose the optimal layer for tracking can dramatically reduce the feed-forward cost for easy frames, leading to an overall speedup. And our policy learning method is trained end-to-end and can be applied to any deep network architecture designed for these time-critical tasks. So thanks.